Hello friends, in this video we will go through with some pharmacokinetics calculation, descriptions and some questions. Now please remember that we will try to stick only with the calculation important for PEBC exam. We are not covering whole pharmacokinetics topic here, just the calculation. So let's begin. First, let's refresh some basic concepts. Like pharmacokinetics is the study and characterization of the time course of the absorption, distribution, metabolism, and elimination ADME of drugs. I always remember this word ADME: absorption, distribution, metabolism, and elimination of drug. This is the basic definition of pharmacokinetics. Then, drug absorption is the process of uptake of the compound from the site of administration into the systemic circulation. In simple words, when the drug is intake or administered in the body and it reaches to the systemic circulation, this process is called systemic circulations mean blood. This process is called absorption. Then we have distribution. Drug distribution refers to the transfer of the drug from the blood to extravascular fluids and tissues. That is, when the drug moves from blood to other tissues, this is called distribution. Then we have drug metabolism, is the enzymatic or biochemical transformation of the drug substance to usually less toxic metabolic product which may be eliminated more rapidly from the body. So it says that when we take the drug, it will not go as it is to the blood, but it converts into its metabolic product first and then move to the blood. Why we convert a drug to its metabolic product? Because we want to eliminate it from the body. Then we have drug elimination. Our final process is the removal of drug or its metabolites from the body. That's the simple definition. Then we have bioavailability, refers to the relative amount of drug from an administered dosage form that enters the systemic circulation. Remember that whatever amount of drug we took, the whole amount will not reach to the blood. Some amount will reserve and some amount will convert to the metabolic product and then reach to the blood. So the amount that reaches to the blood after its metabolism is called bioavailability. Drugs bioavailability factor is represented by F, which represent the decimal percentage of the drug substance available, may be used to calculate bioavailability. The value of F may be 0, indicating no absorption, to the maximum of the value is 1, indicating complete absorption, and this value, that is 1, is when we took the drug by IV dose. Then we have an example of bioavailability question. If the bioavailable factor for a drug substance in a dosage form is 0.60, how many milligrams of drug would be available for absorption from a 100 milligram tablet of the drug? Simple calculation, if we have 100 milligrams and the bioavailability factor is 0.60, then we multiply it and then we got 60 milligram. That's the dose of drug. Then we have another point to clear is bioequivalence. We say two products are bioequivalent when they produce same effect or they show same bioavailability. Um, their dose may be different, their dosage form may be different, but if they are producing same effect and they are giving same bioavailability, then they are called bioequivalence. Bioequivalence is a term in pharmacokinetics used to assess the expected in vivo biological equivalence of two proprietary preparations of a drug. If two products are said to be bioequivalent, it means that they would be expected to be, for all intent and purposes, the same. In simple language, if they are producing same effect, then they are bioequivalence. A question: if the bioavailability F of digoxin in a 0.25 milligram tablet is 0.60, this is the amount of tablet, the amount of digoxin, and this is bioavailability. Compared to the bioavailability factor of 0.75 in a digoxin elixir is 0.5 milligram per ml. Calculate the dose of elixir equivalent to the tablet. So first calculate the amount of bioavailable digoxin in tablet. We have the amount of digoxin 0.25 milligram, then we multiply it with bioavailability factor, we got 0.15 milligrams. Next we will calculate the bioavailable digoxin per milliliters in the elixir. So the bioavailable factor was 0.5 milligram per ml, and then we multiply it with the amount of digoxin, we got 0.0375 milligrams. Then finally we will apply dimensional analysis, determine the quantity of elixir that will provide 0.15 milligram. 0.15 milligrams means here because this is the amount of digoxin in tablet. So 0.0375 per milliliter, then how much? 0.15 milligram in how much milliliters? When we calculated, we got 4 milliliters. Next, in this chart, we will discuss 3 points. Try to understand 3 points. This is the peak of concentration of a drug reaches in the blood. This is called Cmax. The time it takes to reach the maximum concentration is called Tmax, and the whole area which is green, this is called area under curve. That is, this is the amount of drug were present in the blood. This is the table that we take with the time, and this is the serum drug concentration. We took this table, this calculation, and then we plot this graph. We can calculate bioavailability by area under curve data. How? Calculate the bioavailability factor of a drug may be determined by comparison of a area under curve data for the particular dosage form against the intravenous form. Why we are using intravenous form? Because if you remember, the F for intravenous is 1. That's the maximum. So the formula for bioavailability with the help of area under curve data is area under curve of dosage form, whatever dosage form we are taking, divided by area under curve of intravenous. Let's see an example. If the area under curve for an oral dose of a drug administered by tablet is 4.5 grams per milliliter and the intravenous dose is 11.2 grams per milliliter, calculate the bioavailability of the oral dose of the drug. According to the formula, we put all the values. When we calculate, we got 0.4, that is the 40% answer. Then we have another concept, plasma concentration of unbound versus bound drugs. The fraction of unbounded drug in the plasma compared with the total plasma drug concentration, that is bound and unbound, is termed as alpha. According to the definition, concentration which is unbound and concentration which is bounded, this is the total concentration of the drug. That's why we put a T here. The ratio of unbound with the total one is called alpha. Let's see an example. If the alpha value for the drug digoxin is 0.70, what would be the concentration of free drug in the plasma if the total plasma concentration of the drug were determined to be 0.7 nanogram per milliliter? So the concentration which is unbound will be alpha multiplied by concentration total according to this formula. We put all the values and then we got 0.49 nanogram per milliliter. Simple example. Then we have the apparent volume of distribution. Why is it called apparent? Because it is not real, it's a hypothetical. Means we estimate it on our own. The apparent volume of distribution for a drug is not a real volume but rather a hypothetical volume of the drug fluid that would be required to dissolve the total amount of drug at the same concentration as that found in the blood. The volume of distribution is an indicator of the extent of a drug's distribution throughout the body fluids and tissues. The information is useful in understanding how the body processes and distributes a given drug substance. The equation to calculate volume of distribution is D over Cp. D is the total amount of drug in the body and Cp is the drug's plasma concentration. Let's see an example. A patient received a single intravenous dose of 300 milligrams of a drug substance that produced an immediate blood concentration of 8.2 microgram of drug per milliliter. What will be the apparent volume of distribution? We have dose and we have blood concentration. We know the formula is D over Cp. D is 300 milligrams and 8.2 micrograms per milliliter is plasma concentration. When we convert it, we got 8.2 milligram per liter. How? We had 8.2 microgram per milliliter. In 1 liter we have 1000 milliliters, and then in 1 milligram we have 1000 micrograms. So this microgram cancel out with this microgram, this milliliter cancel out with this milliliter. When we calculate everything, we got 8.2 milligram per liter. I showed this step in my previous videos. If you don't understand here, please go to my previous videos to understand it in a better way. Then we put everything in the formula. We got 36.6 liters volume of distribution. We can also find the total amount of drug with the same formula of volume of distribution. Let's see how. 4 hours following the intravenous administration of a drug, a patient weighing 70 kg was found to have a drug blood level concentration of 10 microgram per milliliter. Assuming the apparent volume of distribution is 10% of the body weight, calculate the total amount of drug present in body fluid 4 hours after the drug was administered. We have formula Vd is equals to D over Cp. When we will find drug total amount of drug, we rearrange it. We know according to the question that the volume of distribution is 10% of body weight. 10% of 70 kg will be 7 kg since its volume, then we write it as 7 liters. Then plasma concentration is 10 microgram per milliliter, which is equals to 10 milligram per liter. Same step as we did in previous question. Then we put everything in the formula and we got 70 milligram as the total amount of drug. Next is elimination half-life and elimination rate constant. The elimination half-life is the time it takes for the plasma drug concentration to fall by 1/2. For example, if it takes 3 hours for a plasma concentration of a drug to fall from 6 to 3 milligram per liter, its half-life would be 3 hours. After 3 hours, that 3 milligram will be reduced to 1.5 milligrams per liter. Remember that in this example, the drug is following first order reaction. And the elimination rate constant for first order reaction is K represent the elimination rate constant and EL means elimination. 0.693 divided by T half-life. Let's see an example. Calculate the elimination rate constant for a drug that has an elimination half-life of 50 minutes. We put everything in formula. Here minutes is in denominator, so to show it we put a -1 here to show inverse. We got 0.0139 minute inverse as an answer. In this video, I only discuss elimination half-life and elimination rate constant just for first order reaction. Now I know that there are many complicated calculations and complicated formulas in pharmacokinetics. I didn't discuss zero order reaction, pseudo order reactions, etc. etc. Why? Because PEBC will not give you complicated questions in exam. They will give you simple questions. Most probably the total amount of the drug and volume of distribution. This is the most common questions which is asked in exam. So don't worry about complicated one. Thanks for watching. Please like, share and subscribe.